Uh, in this talk, I would like to consider the shredding one-dimensional shredding operator with a decaying random potential, and would like to consider the level statistic problem. We consider two models. The first one is a decaying potential. And if I have a time, then in the second section, I talk on about the different model, which is the decaying coupling model. Results are kind of similar, but a bit different. So, okay. So the first decaying potential, the shredding operator with a one-dimensional, as T is a space variable with some potential, which has a kind of Russian school model on a real line. Where AT, this is a smooth, and this is a decaying factor. And F, this is a kind of a random potential. And XT is a Brownian motion, so this is a kind of Russian school model. More precisely, A is a kind of smooth function, and even function. This is not so essential, and decaying. As a decay rate is t to the minus alpha when alpha is positive as t goes to infinity. So f is some smooth function on a torus, or can be a Riemannian manifold, such that for technical reason the integration of f must be 0. Xt is a usual Brownian motion on this torus. So first, I would like to describe the spectral property of this operator. Because potential is a compact perturbation to the Laplacian, so we are interested in the spectral property on the positive real axis. There's a result by Professor Kotani and Shiroya in 1988 that spectrum on positive half line changes the critical decay exponent alpha. Alpha is the decay exponent of the decaying factor. 1/2 is the boundary. So if alpha is sufficiently large, I mean rapid decay, then spectrum is AC, and alpha is small, I mean a slow decay, then spectrum is a pure point with exponentially decaying eigenfunctions. And what is most interesting is a critical case. I mean, alpha is 1/2. Then you can explicitly find some critical value such that spectrum changes between EC. I mean, lower energy less than EC, we have a pure point spectrum, or above which we have a singular continuous spectrum. So this is one of the very interesting models which have some transition of the. I'm sorry. Yes.
This one actually get exponential decay. I mean, doesn't the Lyapunov exponent go to 0?
It's a kind of. It's some x, but it x some power. Yes. So it's kind of exponential decaying, but not exact. Thank you. So people would think why 1/2 is critical. I mean, I have one comment that if RT theta t, let R theta is a prefer coordinate, which I will describe the definition later. Then we can see that log of RT, the leading order of which can be written something like AS times some bounded functions and stochastic integration. So log of RT, it can be a time change of some Brownian motion, so that the behavior of RT, it depends on square of AS. This is finite, then R is bounded. That's why in this case we have a AC spectra. This is a kind of central reason why 1/2 is the critical. Okay. So in this operator, I would like to formulate a level statistic problem. This is some of you is very familiar with this level statistics. The motivation is to study the distribution of random eigenvalues. To formulate the problem, we would like to consider the finite version. I mean, let HL is a restriction of H into the finite box of length L with Dirichlet boundary function. Then we have countably many eigenvalues, but because I am only interested in the positive eigenvalues, so I ignore the negative one. Let n0 is the smallest positive one. Let this is eigenvalues, positive eigenvalues of HL. So in the level statistic problem, we do the following. If we write the eigenvalues like this, then as L goes to infinity, then the spacing of this is something like 1/L. Because in this Hamiltonian, the density of state is always bounded. So if L goes to infinity, each eigenvalues are squeezed and dense in the real axis. And because I am only interested in some behavior of eigenvalues on the vicinity of one fixed E0, this is arbitrary, and I take this is any real positive number in E0, which I mean, I would like to study the distribution of eigenvalues near E0, which we call the reference energy. Sorry. to study the eigenvalues near E0, we would like to consider we consider the d-scaled eigenvalues. So if we consider the difference between these quantities, then it will go to 0. So I multiply L. It goes to some order 1 quantity. But because our density of state of our Hamiltonian is not constant, then I mean the density of eigenvalues differs if we change reference energy. So we take the square root of that because square root of divided by E. This is the integrated density of state in our Hamiltonian. So we scale with respect to the integrated density of states so that we expect that the limit of the point should be the stationary. This is kind of called the unfolding of eigenvalues. So we consider the points of this and take the limit of L to the infinity. To formulate this one, we consider the random point process whose atoms are given this quantity. So this is Schr. This is our study. So our question is that as L infinity, we study the behavior of Schr. This is our question. So I recall the known result. We have only 2 results so far on this direction. First one is by Philip and Stoichkov in 1998. They consider the so-called CMV matrix. CMV matrix is a kind of random unitary ensemble. And so that the eigenvalues of which is living in the unit circle. They consider a kind of CMV matrix with a decaying potential. And the result is like this. If the rapid decay case, Schr goes to a clock process. And if alpha is less than 1/2, slow decay case, it goes to Poisson. And in a critical case, it goes to a limit of a circular beta ensemble. So this is a very beautiful result that depending on the spectral property, the AC spectrum case, point process goes to clock process, and the pure point case it goes to Poisson, and critical case it goes to something coming from the random matrix theory. So one of my motivation is to consider the same problem in the case of the Schrödinger operator in the continuum. But for the Poisson case, No, I do the second. Second one is Khrushchevsky-Barkovirac. Yes?
What's beta depends on?
I'm sorry?
Beta, the limit.
This is the beta. How beta depends on. Yes, this is coming from, in this CMB matrix, this is coming from, in this case, matrix decaying like something like this, and this is some constant. And the beta is a function of this constant. So in this case, Khrushchevsky-Barkovirac considered one-dimensional discrete Schrödinger operator, and alpha is decaying potential, alpha 1/2. Then their result can be translated in a setting that QCL goes to sine beta process. Sine beta is a kind of limit of Gaussian beta ensemble.
I'm sorry. This is probably so. This is not this limit. This is not the same object. The limiting process for the limiting process for circular beta ensemble.
Good question. It turns out to be the same. Not clear in this stage. So this result is also interesting. They considered only the critical case. My method maybe can be used to Schrödinger operator to the clock process. And for the Poisson case, in the Schrödinger operator in the Poisson case, I guess in the method by Frederick Kropp can prove this statement even in the random Schrödinger operator with decaying potential. Today in my talk, I will concentrate on this rapid decay and critical case. Okay. So I go to the our result. For the first decay, alpha bigger than 1/2. This is a kind of close to the free Laplacian. So let us consider the free Laplacian at first. A is 0. Then En is explicitly computed. So that the atom of this point process, the least scaled eigenvalues which we would like to consider, this is equal to n pi minus square root of E0 times L. So if I varied n, so it's a kind of a point n pi with some translation. But if it does not converge, then the point process does not converge. So to have a convergence of the point process, this square root of E0 times L, this should converge. Modulo pi. In other words, we need to take subsequence to have a convergence to the first decay. This is for the first decay only. For that critical case, we don't need to take subsequence. No. This is in another representation, in other interpretation. In the first decay case, the generalized eigenfunction doesn't decay. generically at infinity, but for the critical case, it's not. So this is the main reason. So I put assumption. This is an assumption for the subsequence. Lj. Lj satisfies that property. I mean, square root of E0 times Lj. This converges up to modulo pi. So modulo pi some mj pi plus beta gamma plus square root of 1. Mj is a kind of natural number, and gamma is 0 to pi. So this is a very natural assumption. So under this assumption, we can describe our result. This is exactly similar to the keep stoichio. The limiting point process. To describe the limit, I use the Laplace transform. F is some good function. XCL F is a kind of the XCF is an integration of F with respect to C. Usual notation. Then the result, roughly speaking, I like the result. There are some probability measure mu gamma such that we have something like this. For some probability measure, on 0 to pi. So this theorem, roughly speaking, the following. So the atoms of the limiting point process living in the home of n pi minus phi. N is all integer, and phi is a random variable whose distribution is equal to the mu gamma, which says that the atoms of limit, this is a kind of n pi, n plus 1 pi, so on. Then atom is described is a translation of n pi to minus p. Everything is the same phi, and phi is a random variable. So this is a kind of very similar to the free Laplacian case. But free Laplacian case, phi is always deterministic. But in this case, we have a random variable. So what is mu gamma? Mu gamma is a kind of can be described explicitly. Mu gamma. This is a distribution of the following random variable. If we take the this is our prefer variable at E0. If we don't have a potential, then this purifier variables equal to square root E0 times t. So this is a kind of perturbation. This is a kind of fluctuation from the free case of the purifier variable. I plus beta. Then it is known that it has a limit as t goes to infinity. So we take the fractional part of this one. This has a sum. This random variable has a limit, known to have a limit. I take the fractional variable, a fractional part, in a kind of fractional part, in the sense of pi z. So mu gamma is a distribution of, so roughly speaking, mu gamma is a distribution of the purifier variable. And a second. So the behavior of this purifier variable depends on the decaying property of our potential. If, for instance, if alpha is less than 1/2, I mean, when it has a sufficiently slow decay, then mu gamma is a uniform on 0 pi because potential doesn't decay sufficiently rapidly, that does not decay fast enough, so that we have a kind of loss of memory property. But we are working on the fast decay case, so this is not our case. In our case, alpha is bigger than 1/2. Then mu gamma is not uniform because potential decaying. So this sorry, it's gamma. So mu gamma really depends on gamma in this case. And I would like to remark that in the CMB matrix case, in the CMB matrix case, in the work of the Kilp Stoichkov, they have automatically have a rotational invariance in the unit circle by the definition of the CMB matrix. So in this case, mu gamma is automatically uniform. So the CMB, it is very beautiful, but for the Schrödinger case, we do not have such kind of property. It's a kind of a problem, and that's why we have to take a subsequence. This is annoying, but we cannot avoid this one. So in terms of the probability theory, it can be interpreted as a kind of a law of large numbers. This is not a law of large numbers, but it's similar. So it is natural to consider the central limit theorem. So as before, I put the eigenvalues in the real line. This is a reference energy, and E of MJ's eigenvalue, where MJ appears in this assumption. MJ's eigenvalue is a kind of closest eigenvalue to reference energy. In fact, the difference of pitch can be written something like minus phi over Lj. Phi is a random variable appearing in the theorem 1. So we write eigenvalues. This is nth eigenvalues counted from this one. N plus 1, something like this. So the theorem 1 tells us that the spacing is something like pi over Lj. So, to consider the second order, I consider following quantity. If we consider the spacing of two eigenvalues, if I multiply Lj, it goes to pi by theorem 1. So I substitute minus pi. So it goes to 0. So I multiply some growing factor. So theorem 2, under assumption A, and I moreover alpha must be less than 3/2, then xj n, it goes Gaussian with a covariance. Covariance can be written explicitly. Covariance between n and n prime can be described by some constant times real part of the integral s to the minus alpha minus pi s times 2 times 1 minus yes. So it's a kind of a very long range correlation. Oh, where CE is a very explicit constant. This is integral in the torus. L is a generator of our Brownian motion on the torus. So f is our function. So this is a resolvent. I take the gradient and integration of the second order. So it's a kind of explicit, and but we know that this is kind of very long covariance, long range covariance. So this theorem 2 says the following. This nth eigenvalue counted from this one, nth eigenvalue. By theorem 1, the first order is equal to n pi over Lj. Second order is 1 over Lj times power Lj to the power alpha plus 1/2, and this is Gaussian. Gaussian J. So this is really like a central limit theorem. So this is a lower ln, this is in CLT term, and this is our power.
Is there a random discrete Schrödinger operator which has this which looks like this limited?
It's a good question. Maybe it should be doable. Yeah, it should be the.
So one without a limiting procedure. Just so kind of the philosophy is that the eigenvalue statistics are described as by some limiting random operator. So the first term looks like eigenvalues of the Laplace of the discrete.
Your question is to consider the continuum limit of this shading operator.
But it's actually, for some strange reason, the limit seems to be a discrete. So this looks like a discrete. Laplace.
Why this is discrete? Yeah, of course this is very similar. I don't know that in the discrete shading operators they have this kind of thing.
No, that's exactly my question. Whether you can construct a random potential on Z so that the corresponding discrete Schrödinger operator will have this. This kind
maybe yes, I agree with you that even for the discrete random shading operator with a decaying potential, we should have the same statement. I had not to study this discrete shading operators, but. I agree that. Maybe I don't answer your question. Let's do later. Yeah, of course, I know that even in the discrete Schrödinger case, some people have the result for this first order term. I think there's some result. But for the second term, I don't know the corresponding result for the discrete Schrödinger case. If you know, please tell me. I don't know. Yeah, but yeah, I know some work that by in the discrete Schrödinger case, yes, or some other. This kind of quantity goes to pi almost surely. It is also in this model we have this result also, and I think some other people study the Jacobi matrix with decaying sufficiently large first decaying potential and have this kind of result. I think I have seen some paper, but I forgot the author of the reference. So. I'm sorry, I can't tell you the exact reference. That this kind of result already exist. But I think they don't describe new gamma. So about that. So now I would like to finish to mention the first decay case and go to the critical case. But for the critical case, I have to prepare some notations. We have two ensembles. So I would like to define the circular beta ensemble at first. Circular beta ensemble is an ensemble on the unit circle. Something like this. Of n point, whose probability distribution is proportional to this quantity. Now, triangle of something. This is a van der Bond determinant. Beta is positive. So this is a kind of ensemble of random matrix theory of n point in the unit circle. And scaling limit of which is studied by Kilip and Stoichkov. So let's theta j goes to 1 to n. Let theta j obeys this probability distribution. multiply n, theta j basically lives in minus pi to pi. If I multiply n, it goes to minus n pi to plus n pi. I consider the point process whose atoms living in this scaled eigenvalues. Take limit. Does this scaling limit exist and hold the limit of circular beta ensemble, which I denote by C beta. And the existence of characterization of this C beta is shown by Kilip and Stoichiev. I write that here. So the Laplace transform of this is written by something like this. Sorry. C1 inverse 2n pi plus theta n so this is a kind of strange looking representation that I have to explain it to you. So it means that the atoms of our limit is, this is our atom. So what is Psi1? Psi is a function of lambda. And this is an increasing function. This is increasing function. Increasing function. This is my notation, increasing function. So this is parameterized by time t. So as t moves, then this increasing function moves. And this is a random increasing function. This is random increasing function with respect to, I mean, for fixed t, this is an increasing function of lambda. T is any number t. Psi1 is this function when time t is equal to 1. So I put the 2n pi plus theta. 2n pi plus theta. I mean the integer multiple of 2 pi plus theta. Theta is a uniform distribution. So on. So our atom of our limit is this point. This is atoms of our limiting point process. So Psi is a solution of the following stochastic differential equation. With initial value 0. So ZT is a complex Brownian motion. So for each fixed lambda, I mean, this is just little bit complicated. For fixed lambda, psi as a function of t, this is a stochastic process given by this SDE. And so for each lambda, we have this Ct. And now it is possible to realize this Pt. Pt is, if lambda 1 and lambda 2, we have a stochastic process, these ones. For any lambda, we have many stochastic processes. But it is possible to realize all processes simultaneously on one probability one probability space. That's why we have makes sense to have this increasing function values process. And this is the keep stoichiof. We don't have enough. A second. This is a circular beta, and we have to define the Gaussian beta. This is famous. This is a point of the real line whose probability density is proportional to the van der Waals determinant times beta times Gaussian term. This is very famous ensemble in random matrix theory, and we consider the scaling limit Gaussian zeta g sub beta, which is the limit of the following point process. So in this case, density, it is also known the density of state is kind of a circular law. So we have to take this one as for the unfolding. In this case, we need unfolding. Then this is a density of state at 0, for instance. Okay. And the characterization of this process is given by the famous work by Valko-Virac. Let n lambda is a counting function. Then n lambda is in distribution equal to the following random variable. This is Ct lambda. This is a different one. This is different one. As t goes to 1. So this is a different function which I described before. As t goes to approaches to 1 from below, it converges to the point of integer multiples of 2 pi. So almost surely it is equal to z n. Sorry. Then this Ct is a the solution of this following SDE. as 0 initial value. So I have to make some remarks. Okay. These we have two ensembles, and limit of them have a very similar but different representations. For the Kilip-Stoichkov, this process is a increasing function, and we can prove that this is a strictly increasing and a continuous function for all t. So this is a continuous function. But actually, this is very hard to prove this fact because we have a singularity of this in this differential equation at t is equal to 0. So it is not easy to justify and to show the existence of solutions of this equation. On the other hand, for the representation of Valko-Dirac, it does not have singularity from t. T goes to from 0 to 1, but not equal to 1. So it's a kind of smooth, so that this Ct is a very good process. But as t goes to 1, then it diverges. Because of this fact, as t goes to 1, it goes to integer. I mean, as goes to t goes to 1, then this process goes to 1. So the limit is not continuous, of course. So it's very, it's very similar, and it looks like that they are solving the same equation from the opposite side. For the usual differential equation, if you solve the same equation for the opposite side, it should be the same. But for the stochastic differential equation, this is very different thing. So because I finished the notation, I go back to our model. Alpha. And then at first, Schr, our point process goes to limit of circular beta ensemble. Second, Schr goes to limit of Gaussian beta ensemble, where beta is beta is a function of our reference energy. This is explicitly given by 8 times E0 over our constant C of E0. C of E0 is already appeared in our statement of theorem 2. And it turns out this is equal to the 1 over Lyapunov exponent, in the sense that but this Lyapunov exponent has a different, something different. That the solution to this Schrödinger equation satisfies the following decay property. So it's a very different meaning of Lyapunov exponent, which is studied by Professors Kotani Ushiroya. But using by this factor, we have the following relation. At the beginning of our talk, I mentioned the following spectra. In the spectra, we have a critical energy under which we have a PP and SC. So my claim is that the beta changes when we pick difference energy from different region. I mean, if I pick difference energy here, then corresponding beta is bigger than 2. If I pick here, then beta is less than 2. And so to the critical energy, it goes to the famous GUE. Actually, this beta E as a function of E, this is a strictly increasing function of E. And it goes to 0. Beta goes to 0 as E0 goes to 0. And as E0 goes to infinity, then beta goes to infinity. It means that all beta can be realized by our Schrödinger operator. So we have a coming the corollary as you asked in the first. By some other byproduct, this limit is equal for all beta. It's just a byproduct. I mean, of course, if you look at the definition of C beta ensemble and G beta ensemble, these definitions are, proportional to the van der Waals determinant. So it's very similar. So we are not surprised to see this. This is very natural. But to be honest, the truth of this fact has not been known. Actually, of course, has been known for specific beta, because in this case we can compute the correlation function or something like that. It could put explicitly so that it is clear that it's equal. But any beta we don't know. Barco and Dirac has a different. They announced to have a proof of this fact. I haven't seen the paper, but I met Benedict Barco, and he told me about it. So they have another proof of this fact. We don't have enough time, so now I'm finishing. So this figure gives us this limit point process, sine beta. Sine beta has a kind of phase transition between beta at beta is equal to 2. But we already know the parallel statement. In their paper, they said sine beta has phase transition at beta is equal to 2. I can write a statement. What does it mean? It's not so clear. Actually, it is not a phase transition as a sense of the point process. But they describe something. It's not that one, but they have another description of the phase transition in sine beta in another case. And I would like to have a final remark. Beta is, goes to infinity. It means that if you look at the definition of the beta ensemble, beta is infinity is that level repulsion is very strong. So it is similar to the AC case. AC case. So our point process C or G or whatever, if beta goes to infinity, it goes to clock process. We can prove that actually. For instance, actually this C, C is equal to beta over 2 or something. If beta goes to infinity, so we do not have the contribution for the diffusion term. So it is very natural to expect this one. And on the other hand, if beta goes to 0, if beta goes to 0, then it is opposite that the diffusion term dominates our this one. Then there are recent results by Ares and Dumas that this is Poisson 2 pi d lambda. This is very recent result. I'm very interested in this paper. So it's, as beta goes to 0, then we have no repulsion. So it is very natural, I mean, to expect this one. Of course, before taking the scaling limit, if beta is equal to 0, then it should go to Poisson. But the important fact of this is that after taking the scaling limit, then beta is equal to, whenever it goes to 0, then it also goes to Poisson process. So these two remarks is very consistent of this picture. Sorry, I did not have time to the another model, but okay, I stop here. Thank you very much.
Yeah, so Valka and Drag, at least what they announced is that they can construct a random canonical system for which the spectrum has this distribution. Does your argument shed any light on how this, how a canonical system, how a random canonical system appears in this limiting procedure?
I don't understand. What do you mean by random canonical system?
In like cranes. So what Valka and Drag announces that they at least announced that they can construct a crane system, which a random crane system for which has this eigenvalue distribution. So my question is there some meaning to discuss operator to couple your model to see where this appears from?
Yeah, as I understand, their result is that they found a kind of Dirac operator that spectrum this pitch of equal to the sine beta process. I think this is your question. But they consider the limit of usual tridiagonal matrix. So and take the scaling limit. So limit is a kind of, they have a universality. If you take, you can take any point from the reference energy. In every case, beta is the same. But this operator is very different. If you take different point, then limit is different. So, the correlation must be very, spacing statistics should be very different in each E0.
The coupling itself could depend on the coupling itself. So there could be a way to couple in the probabilistic sense the system in a way dependent on the energy So there could be some strange operator.
Yeah, this is of course I agree to this with you, but I guess it should be different one. It's a Dirac operator. Yeah, it's a good point, and I have not studied it yet.
Other questions? So if you replace this Russian model, I mean the Brownian motion model, by some other underlying random potential, can you do parts of this?
Part of this, for instance, for theorem 1 and 2 is almost the same. For the theorem 3, I don't think it is so easy, because if you consider the same problem in the case of the alloy model in, for instance, continuum setting, then I think it is not so easy because this model has a very good property that you can use some martingale analysis technique. This is very powerful. In the alloy type model, you can use it's still discrete martingale, but as I studied a little bit, it does not have very good property like this. So I guess you can prove in the, for instance, the continuum model alloy type. I think we can prove that it is possible to the second statement for the alloy type. I think it's possible. But to prove the first statement for the Kilip-Stoichio, I think it is very difficult because I erased, but you have seen the theta in the case of the limit. You have a uniform distribution. If you remember the representation by Kilip-Stoichio, they have a uniform distribution. And from this, this uniform distribution must be independent by this CT in their representation. To prove these two facts is very difficult for the Schrödinger operator. CMV matrix, this is automatic. But for the Schrödinger operator, to prove this fact is very difficult. In this Russian school model is a very nice model that we can manage to prove that for that model, it's very difficult for the first statement. Yes.
Yes?
So if you make several somewhat interacting lines, would you actually expect something like compound C beta, or could it average out to have?
You mean if you change the model?
Yeah, so you make several lines and maybe
Yes,
some
you mean the
place
because
and
the
you let them
strip.
interact.
Strip. You mean, for instance, to consider strip or something like this?
Yeah, you make L2 of R into Cn, so, right? You have maybe you can think of internal spins and you let the spins interact.
In this case, we just study the scaling limit of the proof variable.
So the proof of variable business is much harder in that case.
Yeah, I mean you have more proof variables.
Yeah, if you maybe it is doable, but it is not so easy. Yeah? Yeah, in the case of strip, if you have a kind of correspondence to the proof variable, then you can do something.
But I mean, I think, for instance, Hislop had some results on compound Poisson, right? In the localization regime. And so I'm just wondering whether there could be something like compound.
Yeah, this is for the Poisson case.
Huh?
This is kind of random Anderson localization
Yeah.
case, random compound case. Yeah, you can do that for the localized regime. Yes, but for you mean your question is what about the critical case? To be honest, I have never thought about it. Yeah, good question. Yes.
Let's thank our speaker again.
Thank you.
Our next talk will start in 30.